Okay, so today we're going to be looking at a particular physics magnetic fields problem. Okay, so in magnetic fields, we have learned about how to use the right hand to define and find out the direction of magnetic force as well as magnetic fields. So the particular two rules are involved is right-hand curl rule, which you have, so for example, a wire that has a strike current and your right hand is trying to grab the wire, which your thumb is pointing for the current direction, and how your finger grabs the wire gives you the direction of the magnetic fields, okay? Also, another rule is, well, the right-hand palm rule helps you to find out the direction of the magnetic force if you place a current-carrying wire in the existing magnetic fields. Okay, a lot of students are sort of like confusing between the concept about using right-hand curl rule and right-hand palm rule. Okay, sometimes you're trying to find out the magnetic force by grabbing the wire, and that's not going to help you. So today we're going to clarify this a bit better using an example. Okay. So first thing to keep in mind is that, well, a current-carrying wire will produce a magnetic field around it. But the thing is, the fields produced by the wire itself will produce no force to the wire itself. Okay? So only if and only if the field is placed to another existing field. So the resultant vector sum of the magnetic fields produces the magnetic force. Okay. So let's just gonna use this example, okay? So suppose there are three identical wires A, B, and C, okay? They are located such a way that an equilateral triangle is formed, which indicates that the distance between AB, BC, and AC for the three wires are exactly the same, okay? So assume that the current for each wire is also the same, okay? So what will happen to the three wires once you have the current? So the first thing we need to understand is that, well, the question asks you what happens to the wires is usually about, well, how the wires will move relative to each other, okay, in this case. Now, a lot of you might be thinking, well, there's nothing going to happen probably, but we're going to figure it out using the right-hand rule. Okay, first thing is, we need to make sure we understand what is the direction of the magnetic fields produced by each wire. So let's have a look at wire A. So if you try to grab the wire, so your thumb must be pointing towards the plane, so to the whiteboard, so that how you grab the wire will give you the direction of the magnetic fields. So the magnetic fields in this case should be clockwise. And we know that if we try to draw the magnetic fields, in that case, it will just keep going as loops of clockwise directions. Okay. Like I said previously, there will be no magnetic force acting on this wire for the fields that's produced by itself. Okay, so what will happen is, because there's current on wire B and C, so because of these existing magnetic fields produced by wire A, so there will be magnetic force exerted on wire B and C because of the existing magnetic field A. Okay, alright, let's have a look at B first. Well, if you try to draw the wires as you go, at some point you may realize that wire B will allow the fields to pass this way. So this is the magnetic fields due to wire A for B. Okay? Alright, what about the magnetic fields produced for wire C? Well, let's have a look. It's also going to be clockwise. Actually, the three of those are exactly the same. They're going to be clockwise, but due to the different relative position, the direction of the field acts on each wire will be different. So let's have a look at the C thing here. So it's going clockwise, but when it comes to here, it will go this way. So this is B, the magnetic fields due to wire C. And also we know that, well, the direction of the magnetic fields is different though, but the magnitude is exactly the same because the three wires are produced in such a way that they form an equilateral triangle. So the distance is the same and also the current is the same. So we know how to calculate magnetic fields. That means that the three magnetic fields produced by each wire is exactly the same in magnitude. Okay, so magnetic fields is also a vector. So when you have two fields acting on one particular wire, this will give you a resultant field, which is the vector sum of the two fields. So when we do that, we try to add them up as using a vector sum. So this should be looking like a field that's pointing directly up. So just try to clarify this. Okay. Right. So this is the resultant magnetic fields on wire B. Okay. Now we're trying to look at the direction of the force produced by this wire. Okay, so basically using a right-hand palm rule, your current will be pointing towards the whiteboard, and your finger will be going upwards. Okay, and then your force is the palm's direction, so that gives you the force is actually to the right. Okay, and that's for wire B. We're going to use the same analogy for wire A and C. So for wire A, for example, it's just maybe in this case we'll just clean this one up. Okay. So what really happens is that for wire A will be exerted by a magnetic force due to the existing fields from B and C. So B is also the clockwise direction, so that in this case, if you try to graph it, it will be pointing this way when it goes through wire A. Okay, so we try to write it. The magnetic fields due to wire B, and then similarly, due to wire C, it will be going this direction. Okay? And then obviously, like I said previously, the resultant field is going to be pointing to the right. Okay. The resultant field on wire A. So using our right-hand palm rule again. So this one will have a force pointing downwards. Okay? Now, lastly, we're going to look at wire C. Let's clean this one up. Okay? And obviously, from wire A, the field is going to go clockwise. But when it comes to here, it will be pointing this direction. Okay? And for wire B, it will just be that direction. Okay? So B due to A and B due to B. Okay? And then the resultant direction will be pointing downwards. Okay? Now if you try to use your palm rule again, so this is sigma B here. So the force will be pointing that way to the left. Now what will happen is we can try to draw this again just to show the force. On wire A, this is pointing down. On wire B, this is pointing to the right. And also wire C is pointing to the left. So to answer previously, what will happen to the three wires? Well, what will happen is the three wires will collide together. Okay? Isn't